Ever worry about being stranded somewhere because your Uber reservation inexplicably disappeared from the app? Or perhaps your bet on FanDuel is riding high, and then it's gone and can no longer be found. Hi, I'm Afzal from Confluent, and these sorts of questions keep me awake at night. I thought we could go take a look and see why these sorts of things don't happen, or at least don't happen very often. Distributed systems like Kafka use replication to ensure data durability. Today, we'll take a look at how Kafka handles replication, how we can monitor it, and then run some experiments to see what happens when things go wrong. To set the stage, some background on why replication is not an easy problem to solve. From an application developer's perspective, the first challenge we have when we have multiple hosts to connect to is choosing which one. Does each client application get a list of hosts? Or is there a dynamic discovery mechanism? What happens if one host becomes unavailable? If we allow clients to connect to any host, we would definitely gain performance, but the synchronization between the hosts would quickly become very complex. What about the response back from the cluster? That is, do we get acknowledgements? Do we get acknowledgements back when all the copies are written? Or just one? The application needs to know this in order to handle retries. On the subject of retries, clients also need to be aware of what delivery guarantees they get. Is it exactly once, at most once, and so on. Back in the cluster, copying between machines is also not so straightforward. Related to the acknowledgements that the cluster sends back to the client, does it send them synchronously? That is, when all hosts have a copy of the data, or asynchronously, when one or more have made the copy, but not all. Perhaps the client wants to decide that based on its own business requirements, since synchronous is oftentimes slower than asynchronous. If we somehow find ourselves in a situation where different data has been written to different hosts, maybe due to a network glitch or some other failure, how would we decide which host has the correct data? A final concern is maintaining exactly which machines are part of the cluster. Machines fail or slow down and fail to maintain a proper copy of the data. How does the cluster and the clients know to only work with the good hosts? When a machine does come back, how does it catch up and become an active part of the cluster again? Many interesting challenges. Let's see how Kafka does it. In Kafka clusters, replication is done at the broker level. Data in Kafka is organized into topics that in turn are comprised of partitions. Brokers manage these partitions. Each partition is replicated across a number of brokers with the number of replicas defined by the replication factor configuration parameter. There is a cluster level default value for it, or we can specify it when we create the topic. The number of replicas must be less than or equal to the number of brokers. And before you ask, no, we cannot have more replicas than we have brokers by putting multiple replicas of the same partition on the same broker. Kind of misses the point of data durability. Once a topic is created, one partition replica is designated a leader, and the others are called followers. Producers publish to the leaders, and consumers, with one exception, also read from the leaders. The follower brokers behave a bit like consumers, and they fetch messages from the leader to keep up. Kafka not only keeps track of which broker each replica of a partition resides on, but also which ones are reasonably in sync with the leader. This is called the in-sync replica, or ISR list. When a broker falls behind, it is removed from this list. This operation is called an ISR shrink. And when a broker comes back and catches up, it is added to the list, which is called an ISR expand. When a publisher sends data, it is replicated only to all in-sync replicas. This is important, and we'll see why later. Replica lag time max milliseconds is the critical setting for deciding whether a broker should be booted from the ISR list or not. If a replica has not caught up to the leader in this much time, then that replica is no longer in the ISR. Setting this value higher will allow us to give replicas more time to catch up and not give us false positives when a broker is temporarily unable to keep up. Setting it lower will allow us to detect failures faster. What we choose really depends on the business needs of our application. A second setting is how far behind, in terms of actual number of messages, a broker is allowed to be before we take it out of the ISR. The two configuration settings can be thought of like this. A broker has replica lag time max milliseconds to be less than replica lag max messages behind from the leader partition. There's one nuance I'd like to point out with Kafka producers and the acknowledgements they get from the cluster when publishing messages. When a producer sends a message and has the Acks configuration settings set to all all in-sync replicas must have the message before the leader sends back an acknowledgement. Usually, the number of in-sync replicas is equal to the replication factor. However, we can choose to set it to less than that with the min in-sync replicas configuration setting. This too can be set at the cluster level or on a per topic basis. For example, here we have it set to 3 while the replication factor is 4. This allows our application to continue working even with one broker down. What happens if we had min ISR set to the actual replication factor and one broker is down? In that case, the producer would get back an error message when it tried to publish data. When would we choose to do this? Because it kind of brings our system to a halt. We would do this when we need the higher durability guarantee of having the data replicated across all the brokers and are not willing to tolerate even a transient reduction in the number of replicas. In applications such as this, we would configure our producer to retry a bit later in addition to sending out an alarm. Now that we have an understanding of how replication works in Kafka, how do we monitor it in the event of failures? Specific to replication, there are 4 main metrics to keep an eye on. The first 2 are the ISR shrinks and expands. Shrinks will tell us when a broker either fails or falls so far behind that it is no longer considered in sync. Expands will tell us when a new broker is added or when one catches up to the leader. When the number of replicas of a partition is below its replication factor, the under-replicated partitions count will be incremented. This is an early warning for infrastructure teams, which they can address, hopefully, before the partition gets counted in our final metric, under min ISR partition count. If the number of replicas of a partition fall below the min in sync replicas configuration setting for that particular topic, clients will no longer be able to write to it. As you can imagine, this warrants escalation to fix as soon as possible. Enough theory. Let's see what this looks like when you're actually running a cluster. All of the code is on GitHub at the repo shown, and the README inside it will explain how to get it up and running. I encourage you to send PRs with enhancements, bug fixes, and whatever else that you find useful. Our first step is to get the environment up and running. Now that we have all of our containers up and running, let's bring up our Jupyter notebook. Before we start on replication, let's just make sure that the cluster is up and running. Check to make sure that there are no topics. Then let's create a topic with a test topic as the name, 3 partitions, and a replication factor of 3. Examining the topic we created, we have 3 partitions. Each partition's leader is a different broker, so nicely balanced. Each replica is in sync, so ISRs for each partition are all 3 brokers. To make sure everything's running as it should be, let's send a few messages. This should run for about 5 minutes. Coming over to our New Relic dashboard, we can see that it's now reporting the number of messages being sent, as well as the fact that we've created 3 partitions. Everything else is healthy. For our first demonstration, let's see what happens when a broker dies. Making sure our topic is still there and the ISRs are as expected. Now we kill the broker. It's dead. What happened to the topic? Well, broker 2 disappeared. Whereas before, broker 2 used to be the leader for partition 2, now broker 3 was elected as the new leader for it. Finally, ISR shrunk to just 2 for each partition. If we look at our dashboard, the number of ISR shrinks went up. The number of under-replicated partitions is 3 because we're below our minimum replication factor, as is the under minimum ISR partitions. What happens if I try to send a few records? I start getting a few errors. The error message says that there's not enough replicas. Why? Because my min in sync replica setting is 3 and my replication factor is also 3. This means that I cannot publish because there simply aren't enough replicas. One way to make our system a little bit more resilient is to let Kafka know that we're okay with one broker being unavailable. For that, we change our min in sync replicas to 2. That is, we want to be able to continue publishing with just 2 replicas. We see that the min in sync replicas is now 2. Now, if we try to send a few records at this point, we see that it's able to successfully send all 10 records. Coming back to our dashboard, you'll notice that while the under-replicated partitions are still 3, The under min ISR partitions went back down to 0, as expected. Under min ISR being greater than 0 is the critical, the sky is falling, all hands on deck alert. The under replicated partitions metric being above 0 is okay for a little, but each occurrence should be investigated. Last piece, let's see what happens when we bring the broker back up again. Our topic configuration is almost back to normal, our ISRs are set to 3, but partition 2's leader is still 3. We could manually reassign partitions, but there is an automated way to do that, and there's a setting that redistributes leaders among the replicas. It is set to true by default in most clusters, and if you wait for about 5 minutes, you'll find that it balances them out. Back on our dashboard, you'll see that the number of expands is up, and that means we've increased our ISRs back to 3. Under min ISR partitions are back down to 0, under replicated partitions also back down to 0. We are now in a healthy state. For our last experiment, we're going to look at transient network failures and how they impact replication. To begin, we create the topic and make sure it's up and running as before. Now what we're going to do is introduce a bit of a delay using the Linux traffic control utility TC. Here, we're asking it to introduce a random delay with a normal distribution. So we'll get approximately 200 to 300 milliseconds. Kafka 2 now effectively has a flaky network interface. Let's run some data through the system. As expected, the number of ISR shrinks and expands keeps going up. With these transient sorts of delays, brokers are being taken in and out of ISRs as leaders find out that their followers are not keeping up. This experiment has two things that I'd like you to take away from it. One, the number of ISRs growing like this implies that you have a very low tolerance for brokers that are even slightly late. If we increase that tolerance, chances are that we'll smoothen out this issue. This doesn't mean that we do not investigate and perhaps replace the flaky network interface. It just means that to keep systems available, our designs should be a bit more robust. Second is the fact that the latency has grown way past the maximum 300 delay that we had introduced. What that means is that a lot of this time is being spent in the bookkeeping of taking brokers in and out of ISR and then catching up. That provides another alert that would show you when a replication issue is ongoing, the fact that your end-to-end latency has gone up. So how can we fix this? Well, the setting which we've talked about earlier, the replica lag time max milliseconds, perhaps if we increase that, we should be able to redo this experiment and not have these failures. The setting is in my Docker Compose and is set to 1000. Let's put it back to the default value. Well, maybe not the default value, but let's make it 10 seconds. We have to restart our cluster. This particular setting is one of those that requires you to reboot the brokers. Start the cluster up and rerun the experiment. As you can see from our visualizations, the number of shrinks and expands stays at 0. The number of under-replicated partitions also stays at 0. We have demonstrated that choosing the right value for this particular setting is key to be able to smoothen out temporary issues. Those were all the experiments that I had pre-built for you. Please feel free to kick the tires and try out different scenarios. For example, you could try to do a rolling restart by bouncing one broker at a time instead of restarting the entire cluster. This might be able to eliminate downtime for your clients while you're upgrading your brokers. To wrap up, here are the main possibilities to keep in mind when dealing with replication issues in Kafka. First, if you have bursty traffic or transient network issues, then tuning the replica lag time will help smoothen out those alarms. Of course, we should get to the root cause of each and confirm that there isn't anything else going on. Changes in your traffic pattern could also be a factor in replication lagging behind. If only a small set of brokers are having trouble keeping up, then perhaps the traffic to each broker is no longer balanced. In this case, the partitioning strategy used by the producer to decide which partition to send which key to may need to be updated. If all brokers are having trouble keeping up, it's probably time to scale up the entire cluster. The last one is actual failures, and these should be caught by other alarms. The key metrics to watch for in replication are ISR shrinks, ISR expands, under-replicated partitions, and under min ISR partition count. When it comes to analyzing the logs, the keywords you're looking for are shrinking ISR and ISR updated too. The configuration settings that you have are the replication factor for the topic, the min in sync replicas setting for the topic, the replica lag time, and the replica lag messages to tune your system. There are a few other settings that affect replication, and these are related to how followers keep up with the leader, but that's beyond our scope for today. Thank you for watching. I hope you have a clearer understanding of Kafka's replication mechanisms and the importance of monitoring. And absolutely feel free to submit PRs or leave comments with your findings. Take care, and I'll see you on the next one.